In this lecture, we begin to apply Gauss's law. We use Gauss's law to calculate the magnitude of electric fields associated with specific charge distributions. In the practical sense, however, you'll rapidly discover that Gauss's law, even though it's fundamental to nature, is somewhat limited as a computational tool. It could actually only be used realistically, at least at the introductory level, to calculate the electric field associated with very highly symmetric charge distributions. We run up against limits, however, if the charge distribution is asymmetrical. We also run up against some limits if the charge distribution has a specific type of finite shape associated with it. However, for highly symmetric charge distributions, using Gauss's law to calculate electric fields can be done quite easily, and it's a very powerful computational tool regardless of its limits. One of the quirks, if you will, about Gauss's law is that you sort of have to know the answer ahead of time in order to be able to use Gauss's law to calculate the answer. You'll see what I mean here as we proceed. Let's go ahead and take a look at the first of our examples. So it says use Gauss's law to find the electric field everywhere for the following. We're going to take a look at parts A and B first. Part A is a point charge Q. We're going to see a brief repeat here of Coulomb's law in just a few moments. And then secondly, the infinite line of charge with uniform linear charge density lambda. So recall the infinite line of charge problem from chapter 21. I devoted an entire lecture video to it. It took 20 odd minutes or so for me to run through that calculation. Here with Gauss's law, however, it's literally just a couple of steps. Okay, now when we apply Gauss's law in these problems and the ones that follow, we're specifically working now with this portion of the expression, where on the left-hand side of the expression, we're going to set up and evaluate our flux integral. So now let's go ahead and take a look at part A. Okay, so for part A, we just have a point charge Q, and recall, of course, from chapter 21, Coulomb's law, that the electric field lines just radiate outwards from that charge. All right, so right here is my Q, and then let me go ahead and draw in some field lines like so. Like this, and this is my charge Q. Okay, now let's say that I draw some sort of random Gaussian surface, something that kind of looks, say, like this. Notice that setting up and evaluating this flux integral for this type of green Gaussian surface would be quite difficult to do. For example, take a look at this point right here on my diagram. At that point right there on the diagram, the electric field would have some magnitude dependent upon its distance away from the charge. And then perpendicular to the green surface like so would be a little area vector dA. So I would have to do a dot product here of E dot dA. And then I would have to do the same thing, for example, say down here. Down here, this is a different distance away from the charge than this point was. So the magnitude of the electric field here is different than it is right here. And then say off in this direction like so, perpendicular to the green surface, is my area vector dA. So I'd have to do an E dot dA here, an E dot dA here, and so on and so on and so on over the entire surface itself, add it all together to get the left-hand side of the expression, and then solve for the electric field E. That would be enormously difficult to do if I was going to do that in a practical sense involving this green shape here on my diagram. So then therefore what I want to do is choose. I want to choose a specific Gaussian surface to make the calculation as easy as possible. Here are the criteria that I want to fulfill, however, for that Gaussian surface. At the surface itself, I want the magnitude of the electric field to be the same value, and I want the area vector dA to be in the same direction as the electric field vector E. Satisfying those criteria would be what type of shape. In other words, what should I choose as my Gaussian surface? Obviously, a sphere. That would look like this. Okay, so once again, let me redraw this. So electric field lines. Like so. Q enclosed is just equal to the Q itself. That's this guy right there. And then let's say that the Gaussian surface here, which is a sphere, has a radius small r associated with it. Because at the surface of that sphere, the magnitude of the electric field is always the same, this then means that when I set up the integral on the left-hand side of the expression, I'll be able to pull the electric field magnitude out from the integral. In addition to that, at the surface of the sphere, the direction of the dA vector is the same as the direction of the electric field E vector. Therefore, the left-hand side of the expression is as follows. Let me go ahead and do the dot product first. Like so. And now, as I said a few minutes ago, the E is constant at the surface of that sphere. So let me go ahead and pull that out of the integral like so. And then we have this double integral itself, the area integral over the surface area of a sphere. Now, to do that double integral, it actually involves what is called spherical coordinates. I know that you're not familiar with this yet. You will see it soon, however, in multivariable calculus. But you already know ahead of time from simple high school geometry what the surface area formula is for a sphere. It's 4 pi r squared. So then, therefore, the left-hand side of the expression of Gauss's law is E times 4 pi r squared. And now all that we do is just solve for E. We're solving for the magnitude of the electric field. So the magnitude of the electric field then therefore is the following expression. Now let's compare this to what we already know about Coulomb's law. And yes, admittedly, we're sort of using Coulomb's law to set up and evaluate Gauss's law to get the answer. We're sort of using the answer that we already know in order to get the answer. Okay, now let's compare it to Coulomb's law. Back in chapter 21, for a point charge, you saw the magnitude of the electric field as the following expression. KQ over R squared. K was just introduced in chapter 21 as it was originally discovered by Charles Augustin Coulomb when he did his experiments, but it's actually part of a more fundamental constant, and that's epsilon naught, the permittivity of free space. K is equal to 1 over 4 pi times epsilon naught. Just compare the two expressions to each other. This is where the units and the value of epsilon naught comes from. K was originally measured by Coulomb, when Gauss, however, a little bit later on formulated Gauss's law, realizing it was more part of a much more fundamental constant, epsilon naught. This then allowed us to calculate epsilon naught, 8.85 times 10 to the minus 12, and then the units themselves come directly from this expression. Recall from chapter 21 that the units of K were Newton meter squared per Coulomb squared. Well, then therefore the epsilon naught units are just the reciprocal of that, which is Coulomb squared per Newton meter squared. So that's where the units of epsilon naught come from. So yes, in part A of this problem, we're sort of using the answer to get the answer. We'll do the same thing now in part B for the infinite line of charge. Okay, so now here's part B. And then right here is the line of charge lambda, like so. Okay, recall from our chapter 21 calculation from Coulomb's law what the electric field looks like. It's radially outwards away from the infinite line of charge and perpendicular to the line of charge. So let me choose 3 points here. Here, here, and here. So right here at this point, the electric field lines look like this. Over here at this point, they look like this. Okay, you have to kind of think three-dimensionally when drawing this diagram. Same thing up here, they kind of look like this. Once again, you have to think three-dimensionally when drawing this diagram. Okay, now let's go ahead and set up Gauss's law. And the whole process, or trick, if you will, in setting up Gauss's law is to choose the correct Gaussian surface, a geometrical surface. What type of surface should I surround the blue line of charge with such that at that surface, the magnitude of the electric field is always the same and the direction of the electric field in the area vector dA is always the same? Can you picture this? What type of Gaussian surface should I choose? If you're thinking a cylinder, you're correct. So now let me go ahead and draw a cylindrical Gaussian surface, like so. like this, and this cylindrical Gaussian surface, we'll say, has a radius r associated with it. So cylindrical Gaussian surface. And now, for example, take a look at the surface itself. Say at this point right here. Right there at that point, the area vector dA that I'm drawing here in blue is in the same direction as the electric field vector here, like so, in black. Same thing at this point here, same thing at this point here, and so on. The E and dA vectors always point in the same direction. And because at the surface of this cylinder, we're always the same distance r away from the line of charge, the magnitude of the electric field is going to be the same. So then therefore, let's immediately write down the left-hand side of the expression in the following way. Okay, and then we get to the right-hand side of the expression. What is the Q enclosed? I mean, after all, the cylinder itself is infinitely long. So then therefore, it's an infinite amount of charge that's being enclosed. How could I write that in terms of the quantities? Well, this is where the density comes into play. Remember that linear charge density, lambda, is charge per length. So then therefore, the Q enclosed is going to be the charge per length multiplied by the length. The length itself, however, yes, is infinitely long. However, we can get rid of the infinitely long length L by getting the value of our surface integral correct. What is the surface area of a cylinder? Not the volume of a cylinder, the surface area of a cylinder. The surface area of a cylinder is, first of all, the circumference of a circle, 2 pi r, and then multiplied by the length L. Like so. And now go ahead and cancel out the length L. Like this, and then solve for E. So the magnitude of the electric field then therefore is the following. Lambda over 2 pi epsilon naught times R. Okay, now go back to the chapter 21 problem that I did involving the infinite line of charge. Here's what I obtained in that calculation in vector form. This expression right here, where z, if you recall, was the distance away from the charge. In this case, the z is equal to small r. Now, when we did this calculation back in chapter 21, it was a vector expression. So let's now go ahead and just write the magnitude. The magnitude is going to be 2 times k, so 2 times 1 over 4 pi epsilon naught, and then times lambda, and then divided by the distance, which is now referred to as r. If you do a little bit of cancellation, you end up then with the following. This expression here, which is exactly the same as it is in our Gauss's law calculation. So yeah, once again, you have to sort of know the answer ahead of time in order to do the answer, or in order to calculate the answer, that is. This is why we teach you Coulomb's law first, the brute force calculation, which then leads us to this more fundamental relationship of Gauss's law. Okay, now let's take a look at part C, which is a problem that you did not see back in chapter 21. I need to move my file. Okay, for part C, we're going to calculate the electric field due to a uniform sheet of charge. So C is what is called the uniform sheet of charge. It's an infinite plane. So it's a planar surface like so that's infinite in extent. It has a charge density associated with it. This is called charge per area, and it's referred to by using the Greek symbol sigma. Sigma is charge per area. So right here, let's say, is a positive sigma like so. What we need to do is set up and evaluate Gauss's law to calculate the electric field everywhere in space. but we're going to sort of use the answer to get the answer. Here's how we're going to use the answer. Let's make a comparison between the infinite sheet of charge, as we're doing here, and now just standing on the surface of the Earth. When you stand on the surface of the Earth, it looks like you're standing in the middle of an infinite sheet. In other words, a perfectly flat surface. And we already know, for example, that near the surface of the Earth, the force of gravity is straight downwards and can be treated as a constant. So then, therefore, by analogy, if instead we have here an infinite sheet of charge, what should the electric field look like? Well, it should be a constant everywhere in space, and it should be, in this case, pointing away from the positively charged sheet. In other words, the electric field lines should just look like this. Like so. So once again, just think of this by analogy. When you stand on the surface of the Earth, okay, never mind the horizon, of course. When you stand on the surface of the Earth, it looks like you're standing in the middle of an infinite plane. And we already know that the force of gravity near the surface of the Earth can be treated as a constant, and the gravitational field lines are just straight down, like so, perpendicular to the surface of the Earth. Same thing here. We have a uniform infinite sheet of charge as positive in this case, so then therefore the electric field should be constant everywhere in space, and it should point away from the positively charged sheet. That is like so. Okay, now that we have a picture of this, now we have to set up and evaluate Gauss's law to quickly find the magnitude of that electric field everywhere in space. Okay, once again, let me just write down Gauss's law. So how do we write Gauss's law here, specifically the integral on the left-hand side first? Once again, we want to choose a Gaussian surface. What surface should I choose to enclose the sheet that makes the calculation as easy as possible? Well, I'll give you a hint. There's actually an infinite number of shapes that satisfy the criteria that we're looking for. However, all of those shapes must have the following features. So for example, let me draw one of those shapes as a cylinder. Like this. Like so. The sides of the cylinder have area vectors, dA, that are perpendicular to the blue electric field vectors. So then therefore, what is the flux through the sides of the cylinders equal to when doing this dot product? It's equal to 0. And then we have what are referred to as the caps. The top of the cylinder here and the bottom of the cylinder here. Each of the caps, by the way, has the same area A associated with it. Right here at the top cap, the little dA vector points like this. It's in the same direction as the blue electric field vector. Down here at the bottom cap, the dA vector points like this. It's in the same direction as the blue electric field vector. Therefore, if I choose a Gaussian surface that looks like a cylinder, the only flux that I have to calculate is through the top cap and the bottom cap. The flux through the top cap and the bottom cap is the same. It's just simply equal to E times A. So then therefore, because I have two of them, the left-hand side of the expression is 2EA. Once again, there is no flux through the sides of the cylinder because the area vector dA is perpendicular to the blue electric field vector. The dot product then gives us 0 for the sides of the cylinder. And then we've got the right-hand side of the expression. How do you write the right-hand side of the expression for the Q enclosed? Well, the Q enclosed is going to be the density, charge per area, times the area. The area down here that's being enclosed is exactly the same as the area of the caps. Therefore, we write charge per area times area, like so, in order to get the Q enclosed. And now we just solve for E. And when we do, we obtain the following expression. This is a constant. So we end up with a constant electric field in all space near the infinite sheet of charge, just as we do when talking about a gravity field here near the surface of the Earth. Now, I said earlier that there's actually an infinite number of shapes that satisfy the criteria that I went through here in this calculation in order to quickly arrive at the answer, just as I did using Gauss's law. Here's another example of a shape that would work. Okay, so once again, here's my infinite sheet of charge. Let me draw some field lines again. Like so. And now instead of drawing a cylinder as I did on the top board, let me now instead draw a rectangular cube, something that looks like this. Like so. So once again, the sides here of this rectangular cube would have area vectors dA that are perpendicular to the blue electric field vectors. Therefore, the dot product would be equal to 0. And then we've got this cap right here of area A, which is the same as this cap right here. And then right here is a little dA vector that points in the same direction as the blue electric field vector as it does down here. So this rectangular cube shape also satisfies the criteria that is necessary to make the calculation. It actually doesn't matter what the shape looks like as long as the sides of the shape here have area vectors dA that are always perpendicular to the blue electric field vectors. And then the two caps here and here have to have the same area. So if I wanted to, I could have drawn a shape that looks like this. Some sort of weird looking amoeba. Like so, as long as the areas A were exactly the same and the sides of this shape here have a dA vector like so, that is perpendicular to the blue electric field vectors. So there's an infinite number of shapes that satisfy the criteria here in order to calculate, using Gauss's law, the electric field due to the infinite sheet. Okay, in my next video, I'll go through a specific application of this, and I'll introduce you to something called a capacitor that we'll get to in detail a little bit later on.